Winners of track 2. Let me just quickly share their official results. So track 2 was essentially selecting 10,000 training examples for which we then trained electro-large models on to see how effective those 10,000 examples were from the existing QA data sets out there. And we can see that our track 2 winners, the team Supersamplers, when compared to training on 10,000 squad examples, outperform quite considerably on the adversarial QA data sets, and they also do pretty well on the track 1 created data sets, both the dev and the test sets. So I'll hand over to Team Supersamplers to present their work, and they of course will also be receiving a cash prize for their fantastic work. Thanks to ML Commons, our platinum sponsors.
Thank you very much. Hi everyone, let me just share the screen. All right, I believe you see my screen now. Okay, cool. Okay, so hi everyone, my name is Michal. I'm a PhD at the Masaryk University in Czech Republic and a sort of a lead of a Supersamplers team. So this presentation will also cover a bit of a background of our submission to the DADC track, which is a part of a larger ongoing work for creating more robust language models, but I believe that this might also be of interest for this audience. So I suspect it will not be a surprise for you that the NLP data sets contains a lot of biases that we might want to circumvent from modeling by our models. So model-centric approaches do this by adjusting the training process by the objectives or other arrangements. In our approach, we attempt a simple data-centric approch, where we simply resample the existing data sets such that the fitting of these data sets might not expose the biases as much. So I will talk about that a bit more in the next slides. So in our methodology, we start by the survey of the literature of the data biases that are reported or might be relevant for question answering. Based on our own experience, we also enrich this list for 3 new types of biases, which we find eventually quite important. We evaluate the significance of each of these biases in a proposed later described methodology and find a majority of the biases actually to be indeed significant. Finally, we follow with dataset resampling such that the worst performing group is supersampled to the same size as the opposite group. This resampling is also a methodology of collecting our DADC track 2 submission that I will mention more in the future slides too. Eventually, we evaluate the impact of the biasing by resampling by again measuring the model bias and by a change of models in domain and out of domain performance. So here's a list of 7 potential model biases that we evaluate for having a significant impact on the prediction quality. So in addition to the 4 biases that were previously already analyzed in the literature, we evaluate 3 novel kinds of biases that we assume from the error analysis of the model trained on squad. These are dubbed as cosine similarity, similar entities, and subject positions. So for instance, I will not go over all of them, but for instance, for similar entity, bias, we presume that the model is perplexed in cases where more than one entity of given question type occurs in a context. So for example, for a who kind of questions, there is more than one personal name in context. However, eventually we find that the model performs particularly bad on questions with no entities rather than more than one entity. For each of these biases, we implement a simple heuristic that can divide the samples into 2 distinct groups by exploiting the specific bias. We evaluate the squad model separately on each of these groups, and using bootstrapping, we obtain distributions for both groups that we use to mark the bias as significant or not. Specifically, we construct 90% confidence intervals for both groups and say that the bias is significant if these two intervals do not intersect. In case the bias is significant, we use the distance between the bounds of these intervals as a significance of the bias. So here's an example of a heuristic exploiting word distance bias. This one splits the datasets into two groups by the closeness of the closest shared word of question and context from the answer segment. So if this segment is closer than a threshold from the answer, its sample falls into the closer group. And if it's further, or in other case, it falls into further group. We find the most distinctive threshold by a maximum difference of model performance between the groups categorized by squad. These are the distributions of the bootstrap performance of BERT-based model trained and evaluated on squad. Bar ticks denote the ranges of 90% confidence intervals, and the bias significance mentioned on the previous slide can be visualized in this case, or in this plot. We see that 6 out of 7 investigated biases differ the model performance significantly, all except the Kate sentence, reflecting on rank on the answering sentence in the context. The most significant biases on squad are related to answer length or to word distances. This chart shows finally a bias significance of the original model, which is a green one, and a model trained on datasets supersampled by each of the biases. So these are the orange ones. We see that the supersampling reduced bias significance in each of the cases. In some cases, the bias is no longer significant, as with answer length and subject positions, but with others, the reduction is not that big. Here we show the effect of supersampling on in-domain F-score by resampling by each one of the biases, which are the orange ones, and also by their combinations, which are the blue ones. Perhaps not surprisingly, the biases mitigation decreases the F-score, but notice that this decrease is within relatively small range, around 1%. Following charts show the impact of out-of-domain performance when resampling the training dataset on trivia, on natural questions, and finally on adversarial QA. We see that in these cases, the debiasing improved the performance on the model trained on squad for multiple heuristics. The size and bias of improvements are mainly different for diverse datasets, though. We argue that the decrease against baseline, despite the measured bias eliminations for some biases, might suggest that these biases are shared among datasets. However, we will need to perform future analysis to draw such conclusions more concisely. To our surprise, resampling by similar entities bias brings average gains in all cases, including in-domain. Here, which is difficult to explain for us, though. Finally, we construct our DADC submission from adversarial QA dataset by resampling our most successful heuristic, which are similar entities. We again tune the threshold specific for adversarial QA and find the optimal value consistent with squad. The gap in performance is the largest between the questions with 0 entities and more than 0 entities. In our submission, we sample all the underperforming samples, getting approximately 7,000 samples, and we fill the remaining 3,000 samples by a random sampling from the other group, the one which performs better. Okay, to wrap up what we have found so far, we have assessed the significance of 7 specific biases of the models trained on squad. We found no standard methodology for assessing the significance of biases, so we introduced an approach based on a bootstrapping that quantify bias significance as a distance of 2 groups separated by exploiting selected bias. We found that 6 out of 7 biases are represented in the squad model significantly. We show that even simple resampling can partially address the model bias and even improve the resulting out-of-domain performance, making this approach usable as a reasonable baseline for more complex debiasing methods. However, sadly, the simple resampling approach does not seem to scale to addressing multiple biases at once. In our future work, we plan to compare the generic debiasing models, such as mixture of experts, to the baseline with respect to each of the identified biases, to see how well can generic methods for debiasing actually elaborate on specific dataset biases. And that's it. If you're interested in the details, you can also get in touch. We will be happy to answer any questions, and or you can take a look into the linked thesis with technical details about the biases and heuristics. Thanks.
Thank you very much, Michal. And I think we have time for one question. Yes, Katerina.
Hi, can you hear me?
Yes.
Hi. Great work. Thanks for the presentation. We also really appreciate the background of your photo. So I wanted to ask you, so you took a sampling approach to solve this problem regarding by addressing the biases of the QA models. So I wanted to ask you if you know how this correlates to the difficulty of the data that you sampled, if they are easy, hard, impossible for the model, or something like that. Because I don't know exactly how these two views or the sample problem are related. So I think that would be interesting.
Okay, yes, thank you for a question. That's an interesting approach to the problem. Well, this term of like a difficulty of a problem is something which is difficult to quantify. However, like from what we can say is what is difficult for the model based on a given data set, because like probably the data set contains some biases which might divide the samples on two categories, the more difficult ones and the less difficult ones, or the ones which the model can model better than the other ones. So we can say that like, or we can identify the difficult groups of samples for a given model trained on a given data set in this methodology, where we just compare the two groups split by the heuristic exploiting given bias. Is it sufficient somehow?
Yes, somehow. No, I just want your final take on, I don't know, because I'm personally working in active learning, so the idea is to acquire uncertain or anyway difficult data to train a model on. So I've seen other data-centric approaches from other workshops in the past, and I'm not exactly sure if the training data that we are supposed to have should be like 90% hard examples, or what should be the ideal ratio regarding easy examples or not. I mean, it's really hard because right now with supervised learning, we just have data sets that already exist. So when you have to create it on your own, I suppose it's a lot harder and you have to take into account these sort of questions. So yeah.
But I mean, if I can further justify, like in this context of active learning, it seems to me that this is a great position for like mitigating the biases right on the way. So if you were to be aware of some existing biases or some inclination of the annotators for the biases, you can first like measure whether the bias is actually there by training the model on the full data set and then evaluating the model on the two different splits. And once you assess that the bias is there, you can then resample the data set afterwards to somehow mitigate the bias.
Yes, right. Thank you so much.
Thank you too.
Okay, thank you. Oh, we have another question. Yeah, let's go for it.
Hi, can you hear me?
Yes.
My name is Justin. I'm a PhD student at USC. I just have a very quick question with regards to this slide. I was just wondering, do you have any information about the distribution of data samples across these two splits? I could imagine, like, for instance, in the word distance cases, there's less or maybe fewer examples where the word distance is actually larger, while there's more that's shorter, just because annotation artifacts makes it easier to create these samples if they're closer. So it might not actually just be like a difficulty problem here, where if they're further away, it's more difficult, but it's whether, it just happens more frequently. So I was just wondering if you had some insights there.
Yes, you're right that by splitting the data into two groups, you're getting two groups of different sizes. So, but this is also something which is projected into the sizes of the intervals. So if the sample size is smaller, then you might get like less coherent distributions. But yeah, it's not always the case. There are other covariates. But like to comment from this experience here, we've only checked the thresholds, which are some kind of parameters of the heuristics for splitting the data set into the two, in the range that would allow us to obtain the groups which are at least of 1,000 samples, because we have done the bootstrapping afterwards of at least 100 samples, and we found the results unstable if we went below the groups which are of size of 1,000 samples. But yeah, like it is quite likely that if we went over this threshold that were allowed to us by these kind of settings, we will also find more significant biases than what we have found here.
Awesome. Thank you so much.
Thank you.
Okay, let's thank the speaker again.